So, ladies and gentlemen, welcome to our regular Monday seminar, today with pizza flavor. And it's my great pleasure to invite Matyáš Křišťan, and he will give a talk on decreasing the verification radius in local certification.
Thank you for the introduction. So I will be presenting the joint work with Laurent Paioli and Janoušek and Josef Exedáček. And so the main question of this topic of local certification is which graph properties can be verified using only local information from each node. So we will be given instances and we will want to know if the graph holds some property or not, decided. And I will show it on an example right away. So suppose that we are given graphs, they can have some nodes colored in red. And the property that we should verify is that each node has a red node in its neighborhood. So it is either a red node or its neighbor is a red node. So in this instance, it holds. And in our setting, what we do is we take a look at a single node, the one that is called here in black, for example, and ask it whether this property holds, what it thinks. So it can say either, okay, this property may hold, or it can say, wrong, the property cannot hold. And we obtain a decision from each node individually, and then we aggregate their decisions like this. If every node says that the property may hold, then the global consensus is that yes, the property holds. And if at least one node says that the property does not hold, then the global decision is that it does not hold. One node can have everything. So, for example, if the instance looked like this, these two nodes would record that they do not see a red node, and that would correctly show that the graph doesn't have the property. So this was a simple example, and let's take a look at how we could certify that a graph is bipartite. So it is not possible just from the point of view of each node. For example, if it would be a very large cycle, no node sees the whole cycle, it sees just some part of the path, and they cannot tell if it's an even or odd cycle. So in order to study more interesting properties, in this model we allow to place some certificates on each vertex. The certificate is a bit string, and the nodes can see the certificates that are in the neighborhood. So if we want to certify that a graph is bipartite, we need just one bit in the certificate. We can basically provide the two coloring, and now each node takes a look, and the color that it has, the bit of its certificate, must be different than what it sees in the neighbors. So this way, if a graph is bipartite, then we can place certificates and each node can confirm it. On the other hand, we also have to show that if the nodes respond okay on each vertex or any certificate assignment, then the graph indeed has to have the property. So in other words, the nodes cannot be fooled by false certificates. So this still works. If the graph is not bipartite, then there will not be a two-coloring. So for example, here is a triangle, so it's not bipartite, but one of the black nodes will see that it is black and its neighbor is black, and this will happen in any bipartite, in non-bipartite graph. So they can correctly recognize that the graph is not bipartite. So in particular, we study a model called local checkable proofs, which was introduced by Goss and Suomela. And to reiterate, we have the certificates. We have something called folder, which is sort of like an oracle that assigns the certificates on the vertices for its instances. And again, if the graph does not have the property, then we can assume that the certificates are false, and the verifier, the algorithm that checks, must be able to defend against it. And our sort of measure of complexity is the maximum size of a certificate on a vertex. So some properties do not need any. The bipartite graph, as we have seen, they need constantly many certificates. And many properties can be certified by locken. That's a sort of a complexity class. We also know that many properties have a lower bound for locken, so it's like the exact asymptotic amount. For example, certifying that some edges are maximum matching or that they are a spanning tree. So we have this sort of complexity landscape in this setting. And at the very end is the complexity of n squared. So any property that can be verified by an algorithm that sees the whole graph can be verified using n squared size certificates, because we can basically take the whole instance and code it into the graph, into the certificate of each vertex. We somehow check that the graph does indeed look like what they see, and then we can run like any algorithm to it. For example, checking that graph has at least 2 automorphisms meets those n squared certificates. So in this sense, it's a non-local problem. So I will go a bit about the more formal objects that are in the local checkable proof setting. So we have the input graph, which can have labels. For example, if we want to talk about certifying that something is an independent set, we use labels and vertices to indicate which vertex is in the independent set and which is not. We often talk about a graph, about like distance R neighborhood of a vertex. That's what the algorithm sees to distance R. Our graph property is assumed to be a subset of graph. The certificate assignment assigns bit strings to the vertices. And we also usually see just like the neighborhood to distance R of the certificates. And our local verifier is the algorithm that checks the node. So on the input, it gets the distance R neighborhood of the graph and also the certificates, and it outputs either 0 or 1. A prover is the sort of oracle that for every graph that has the property must assign some certificates, and those two work together. So a proof labeling scheme is a tuple of the verifier and prover that work together. The prover assigns the certificates for the verifier. For each graph that has the property, at least one assignment of certificates must be accepted by the verifier. And for every graph that does not have the property, every assignment of certificates must be rejected on at least one vertex. So this is our setting. And another concept is the visibility radius. That is how far the verifier can see. And some properties may require different sizes of certificates for different distances. For example, if our property is that each vertex has a red node within distance 10, and it's easy to certify if we actually see to distance 10. If we see just to distance 1, then we will definitely need some certificates and it becomes more complex. So now we are getting to the question that we study in our paper, and which is if we are given a proof labeling scheme with radius r, how difficult is it to decrease this radius? Meaning how much the certificates will have to be larger. So this is the same thing as before. So what we will basically show is like a general procedure that for a given proof labeling scheme with some radius r produces another one which has works for the same graph property, but the radius is decreased by some small delta. And the idea how to do that is to basically have some helping procedure, which for each vertex encodes the distance neighborhood to the certificates. So here is a rough illustration. So basically, originally the V node saw to distance R, but now it sees only to R minus delta. So the idea is that this now missing information will move to certificates. So now one difficulty is that if it is in the certificates, we cannot be sure that it is true. So there has to be some certification going on. And the idea is not super complicated. The idea is that every node will simulate sort of a broadcast of its neighborhood into distance delta. So then vertex V will be able to see something after distance R minus delta, then see the certificates from the nodes in distance R, and use the certificates to compute the whole R distance neighborhood. We need to do something extra so we can certify that this is correct. And the idea is basically that if the node broadcasts some information, we keep track of the distance of this information from its source. And then we can show that for distance 0, this information must be correct because it's checked by the node that sees the source of the information. And then sort of inductively, we can show that if it's correct to distance k minus 1, it propagates correctly to distance k by just checking that it's the same along the edges. So this is one part of the paper, and basically we take this constructed R distance neighborhood. We basically compute what the graph and the certificates would look like, and then we feed this into our original verifier that sees to distance R, and use that as an answer. Then for definition of the prover, as I said, we just encode the neighborhood and attach the certificates of the original prover. So it basically simulates how the original distance R schema worked. So this is sort of more technical, and for the people that work on this, it was not like super surprising. But we also show a lower bound for this. So roughly the overhead that comes from decreasing by small delta is this large delta minus 1 to small delta, which is where large delta is the maximum degree, and this is roughly like the size of the neighborhood. And this is ignoring some factors which appear there, like we need some log n for the representation of the vertices. We have to include the original certificates, which is Sn, and we need to include some representation of labels, which is Ln, and it works only for degree greater than 3. But that's not super important. So on the other hand, we show that this procedure is close to optimal, and we show a lower bound on how much the certificates can be decreased if we want to decrease the radius. Sorry, at least how much the certificates have to increase. So the idea will be that we can design some artificial graph property. We will design our own certification schema for it and show how much bits it uses. And we'll also show a lower bound for this property. So the idea is that if we start with our proof labeling schema and we want to decrease its size, it cannot go below the lower bound that we will show. So in general, any procedure cannot be better than that. So this is what a graph from the property looks like. So it's like so we keep like free the large delta. So like the internal vertices can have any degree which we choose, but everywhere the same. We have one root of degree 2. Then we have like those complete delta array trees, and we use the labels to write some strings on the leaves. And the left and right subtrees from the root have to have the same size. So the idea will be that we will want to certify that the string in left subtree and right subtree are the same. And intuitively, this is like a lot of information, and it will sort of like have to travel through the root. So that's the rough intuition behind it. And this lot of information will need a lot of certificates. One detail is that if we do it just like this, then it's not clear like which string is represented by these, because they can be reordered. So we use the labels also to set the ordering of the like the children of each node. So we also require that there must be permutation and so on. So we place like constraints on the property that allow us to uniquely define one string from the instance. Okay, so this is like a rough sketch of the proof. So in simpler terms, we will show like how many bits will the certificates need for this instance, or how much suffices by constructing the proof labeling schema. The important part is that by decreasing the radius, the size of certificates decreases exponentially, which I will show a picture and it will be clear. Then we have like a lower bound term which is pretty close in asymptotic terms, except there is this like one gap of r and r minus 1, and here is an epsilon. And then, as I said, if you want to decrease this number of bits, then it's gonna go below the lower bound. So it says something about like every procedure that does this. So the way to certify this procedure is simple. So we can, on the certificates, we can basically write the whole string in the subtree, like it is here. Each node then just has to check that the string that's written on it is concatenation of the strings that are in its children. So this is what everyone does. And at the end, takes a look if the string on the left and on the right is the same. And based on this, rejects or accepts. And everybody else like accepts by default, unless something else is broken. And the size of certificates is this. And you can see that if we like increase the radius by 1, then we can cut the size of the certificates by half.
I just wanted to ask, like, so the vertices, how do they know which direction is the root, or what is the product node and what is the child?
So well, I don't show this, but they also propagate this in the certificates. So
Okay.
we have also enough space to propagate like the distance from the root, which is easy to verify. Yeah, but thank you for the question. So here the root can look further into the children, and so like the size of the certificates is cut like exponentially to the distance that it looks like. So the size of certificates come out from it. So this way we have now shown like how we can certify this, and now we show a lower bound on certificates for this particular property. And the idea is that suppose that there is a working proof labeling schema that uses less than like the amount that we assumed, and we will show that such verifier will always be full in the sense that we can construct something that is a no instance, but it will accept it. And the idea for that is that we will find two S instances which we can somehow cut up and glue them together into something that is no longer S instance, but it looks from each vertex the same. So for that end, we define an equivalence relation between the instances and say that two instances are equivalent if within distance R from the root, they look the same, including the assigned certificates, and also the total number of nodes is the same. And then we just want to show that there will be two instances that have different strings in their subtrees, but they are in an equivalence relation. And that comes just to some counting argument. So we know that the number of strings in the left subtree is like at least this, because in the left subtree that's a quarter of the node, at least. And we show an upper bound on number of the equivalence classes, and that's basically the number of different strings which can appear in this top part. And also we have to take into account the various label assignments, but only the number of different certificates is important because that has n as a variable, and the rest is basically just a function of the radius and large delta. So, and those are fixed for us. So from that we get that there are at least two instances with different strings, but they look the same at the top. So basically you just construct an instance, but by taking the same top and left subtree from one and right subtree from the other. And this is no longer an instance, the two strings are different, but it just remains to check that from each node in this instance, it looks exactly like some different instance. And if this is a yes instance, the algorithm has to have answered yes on every node. And for the same input here, it also has to answer yes. So in particular, from no point, it will see like the blue subtree and green subtree at the same time. So this is an instance that is incorrect and it accepts, so it cannot work. Okay, so to summarize, we have shown how we can decrease the visibility radius at the cost of increasing certificates. We have shown that this cannot be improved by much up to some gap. We include that on some specific graph classes we can do better, for example, on paths. And what questions are, of course, what about different graph classes? But what is a long-standing open problem is a bit different question. What if we have proof labeling scheme and we want to decrease the certificate size at the cost of expanding radius? So this doesn't connect with this actually much. The results do not transfer. And it is solved, for example, on grids and on trees, but it is open in general. Okay, so this is everything for me. Thank you. Thank you very much. I have 4 comments.
So I wanted to ask, because this certifying within bounded radius, that's pretty much close to what is first order property. This that that I allow you to build some extra certificate. It's like allowing you to to adding like there exists a predicate like unary predicate on the universe, a unary predicate such that this first order formula is satisfied in every vertex. Is there something like that, like not really caring about the radius, but maybe caring about the length of the formula that you have to like satisfy it in the vertex or something like that?
So I don't know exactly about that. I know people have studied the connection of like model checking and local certification. It is known that for example, using lock and certificates asymptotically, we can certify, I think, any property when we are on graphs of bounded tree depth. So there is this kind of connection, but I don't think, I don't know if it answers your questions. I'm sorry, I don't know.
Yeah. I don't know what's my question.
But people look at this connection with logical formulas for graph properties.
I do have a one question. So at the first slide, there was this introduction of the model, like you want to, maybe not first slide. Yes, this. No. One back. Yes.
Yeah.
If the verifier says okay on each node, then the global decision is yes. If the verifier says wrong on one node, then the global decision is no. So I mean, does it make sense to introduce some model where I want like the majority to have okay on each node, and then the global decision is yes? So like maybe.
I have not seen that in the literature. I think it can get difficult because you could basically take like independent instances.
I mean, this is then probably not very local. This is some global.
It is a bit. So I mean, this is also global, like at the end.
Okay.
But I think one difficulty could be that you could take basically independent instances, put them next to each other, and then skew the decision like any way you want, sort of. So I'm not sure if you want to certify something like.
Or
I mean, depends on
some simple binary or on instances to compose the result of like.
So this is a bit like AND. So so I think this is actually like an end of all the decisions.
So typically you assume graph property to be hereditary. So this doesn't have to be hereditary. So
I'm not saying that my question makes sense. I just got this idea when I saw this slide. So.
I think maybe if you ask something, if something holds like or at least 1/2 node or something like, then yeah, so that's something.
There are these.
Oh,
okay. So maybe let's do some discussion now. Okay, so that's it. Thank you again.